students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we are going to study line impedance of a transmission line. So, continue. That is, first of all, the definition of a line impedance. The line impedance of the transmission line is what? It is the complex ratio of the voltage phasor at any point to the current phasor at that point. So, if we know about the impedance in general terms also, it called as the ratio between the voltage and the current. So, when we define in terms of the transmission lines, so also it is equal to the voltage phasor at any point to the current phasor at the that point. So, it is defined at Z equal to Vz upon Iz. So, here we have the one transmission line diagram. So, it is the just for your remembrance, because further we will encounter with this expressions. Zs sending end, Zr receiving end, Z0 equal to the characteristic impedance of the transmission line, Is incident and IL at the load end. So, and ZL is the load impedance. So, these are the terms about with which we get encountered further in the derivation of the line impedance of a transmission line. So, if we are remembering that the voltage or current along a transmission line is the sum of the incident voltage plus the reflected one. So, what is the incident wave? Incident wave is terms in the terms of V plus and the reflected as the V minus. So, incident reflected V plus V minus. Incident wave in the it will keeps on decreasing in the exponentially, that is why e to the power minus gamma z, and reflected wave will be opposite to that, e to the power gamma z. And I know definitely you know about the gamma. Gamma is our propagation constant, which is equal to what? Alpha plus j beta, and alpha is our attenuation constant and beta is our phase shift. Similarly, when we write the current in the form of a voltage, we have to also write in the term of a current. So, in the terms of current, it will be incident plus reflected, and of course, when we know I will be equal to V upon Z naught, and Y naught is equal to 1 upon Z naught. So, we can write it as V Y naught. So, same thing is here, Y naught V plus e to the power minus gamma z, and the complete expression of V here, and simply we have to add on Y naught. When we talk about the sending end is what? Sending end from here, this is our sending end. So, when we talk about the sending end, in the sending end what is equal to 0? Our z is the distance. So, z is equal to 0. So, in that case, when z is equal to 0, what will be the change in the expression of 1 and 2? When we substitute this z equal to 0, that means this whole expression containing the exponential function will be equal to 0, because exponential e to the power 0 is equal to 1. So, what we have? We have just V plus V minus, and what we have here? V is equal to current into impedance at the sending end. I have shown you that impedance at the sending end is Zs and the current is equal to Is. We will conducting this to, we will get the voltage across the sending end. So, what we have? Is into Zs and the remains V plus V minus. And when we write about the I, so I can be written as I should be equal to Y naught, of course, Z equal to 0. So, the expression, this expression and this expression will be equal to 1, V plus minus V minus. In the place of Y naught, what we are able to write? 1 upon Z naught V plus minus V minus, and in the place of I, when we take the consideration at the of the sending end, I should be written as Is. So, Is into Z naught should be equal to V plus minus V minus. And when we solve this equation, this two equation, we are able to get the value of V plus and the V minus. So, I will solve one for you. So, first of all, you just add this two equation. So, what we are on adding, what you are getting, Is Z naught plus Is Zs Is Z naught equal to V plus V minus plus V plus minus V minus. This 2 will be get cancelled, and what we are having, 2V plus is equal to Is we can take as common, Zs plus Z naught. So, what will be the expression of V plus? Is upon 2, this 2 will come in the RHS side, Is upon 2 Zs plus Z naught. So, this expression we have achieved. Similarly, by subtracting this two equation, we are able to get the expression for V minus, which is equal to Is upon 2 Zs minus Z naught. So, students, all of you should solve this by the instruction provided by me, that is, you should subtract this equation for getting this expression of V minus. You are able to get the expression of both V plus and the V minus. Now, what we are having? Substitution of V plus and V minus in equation 1 and 2. Now, we have this two equation V plus V and I. So, now what value we are getting of the V plus and the V minus, we just substitute on this equation 1 and the 2. On substituting, we are able to get this expression. And when now the further is the, we have to find out the line impedance at any point Z from the sending end. Remember, a further expression we were able to find out the line impedance from the receiving end also. So, this is the expression of the line impedance of any point on the Z line from the sending end, which is our from the where the signal is sended further. So, now we are having this expression, and for finding the impedance, what we have to do? We have to take ratio of V upon I. So, if we take the ratio of V upon I, just take the ratio, V upon I should be equal to Z, and next one is what? Is get cancel, 2 get cancel, and this Z naught will be comes on the numerator side. So, we are having the Z naught here, and other expression will be simply copied. There is no difference in the expression. Zs plus Z naught e to the power minus gamma Z plus Zs minus Z naught e to the power gamma Z, Zs plus Z naught e to the power minus gamma Z minus Zs minus Z naught e to the power gamma Z. So, this is the equation of the line impedance at any point Z from the sending end. This is one first expression, or we can say that one of the expression of the line impedance. And for example, if we want to find out the line impedance at the receiving end in the terms of Zs and the Z naught, that is impedance at the sending end and the characteristic impedance, of course. When we talk about the other methods of finding the impedance from the receiving end, in that case, in the place of ZL, we will take ZL. We will talk about the ZL in the terms of ZL and the Z naught. But here we are calculating the line impedance from the sending end. That is why the impedance at the sending ending is taken into consideration, which is our Zs, and Z naught will always remain. So, for finding the impedance at the receiving end, what we have to substitute? We have to substitute the Z here. You are able to see the Z. In all expression, we have a Z expression. So, substitute Z is equal to L, and when we substitute Z is equal to L, you are able to see, just I have substituted in the place of Z this expression with the L, and we are able to get the line impedance at the receiving end when we are known with the terms of Zs and Z0. So, one question comes in your mind कि if we are able to get the impedance by this method, so why we are moving towards the alternative method? The answer is that कि when you are provided with the sending end impedance, that is input impedance, then you should use this formula. But there will be some cases when you are not aware with the sending end impedance or the input impedance, and you are aware with the load impedance, then what will you do? In that case, you have to move yourself towards the alternative method. So this alternative methods are for the condition when you are have the load impedance and you are not available with the input impedance. So, at Z equal to L, if we want to express the terms in the terms of ZL and Z0 at Z equal to L, what we will do? VL, the voltage, and V will be equal to IL into ZL, and this is equal to V plus e to the power minus gamma L plus V minus e to the power gamma L, and we know current will be equal to 1 upon Y naught V plus, this is the general expression, and this general expression, these are the general expression which we are so in this condition when we are from the load end, from the receiving end, this expression will be L, Z should be equal with the L, Z will be replaced with L, and we have this expression IL ZL, and we know 1 upon Z0. So, what is the expression here? Y naught is in the numerator side, sorry, Y naught is in the numerator side. So, it will be 1 upon Z0 here, V plus e to the power minus gamma L minus V minus e to the power gamma L. So, at the load impedance, current will be IL into Z0 is equal to V plus e to the power minus gamma L minus V minus e to the power gamma L. And now, solving these two equations by the same method, that first what we have to do? When we have to find out the value of V plus and the V minus, the first thing we add these two expression, and when we add these two expression we will get the value of V plus, and when we subtract these two expression we get the value of V minus. So, by adding and then these two expression and then subtracting, what we are able to get? V plus is equal to IL upon 2 into ZL plus Z0 e to the power gamma L, and when the two expression which are shown in the last slide are subtracted, we are able to get V minus is equal to IL upon 2 ZL minus Z0 e to the power minus gamma L. So, what will be the next step? The steps remain the same as we have used for the calculation of line impedance from the sending end. After that, what we have done? We have substituted this value in the equation 1 and 2. So, right now also we will do the same thing. We have this value, we will substitute the V plus and the V minus now, which we are getting now at this expression, and on substitution we are able to get this expression, and we are letting Z equal to L minus D. Okay. So, this is our expression, and now I will ask you that what is the next step. So, what will be the next step? For calculating the impedance, we will have take the ratio of V upon I, and when we take the ratio of V upon I, IL get cancelled, this V upon Z, V upon I should be replaced with Z, that is impedance of the line, and this 2 get cancelled, and this Z naught will comes to the numerator and other expression will remain the same and will be written. So, here we are getting what we are getting, this is the another expression of the line impedance in the terms of what? In the terms of the impedance in from the receiving end. So, what is the change here? In the first expression, we have taken the ZS and the Z naught for calculating the impedance, and in this case we are taking ZL and Z naught. So, be very precise to when to use which equation. When you are available, again I am repeating, when you are available with the values of characteristic impedance and the input impedance, then you should use the first expression of the input line impedance, and when we are not available with the input impedance and we are available with the what? Our load impedance and the characteristic impedance. So, in that case you should use this expression. So, when the line impedance at the sending end can be found from the above equation. You are able to find out in the last expression, we are able to find out we have shown that if we are available with the line impedance with respect to input impedance and the characteristic impedance, we are able to find out the impedance at the receiving end. So, now if we are available with the impedance equation in the terms of the load impedance and the characteristic impedance from the receiving end side, then we are able to find out the line impedance at the sending end also. So, this equation, and for that what we have to do? We have to let D equal to L. When we substitute D equal to L, we are able to, because what is the complete length of the transmission line is L. This equation can be simplified also. We have the equation or two equations available with it, but there exists one more equation of the line impedance, and that is in the terms of sine and cos, or we can say in the hyperbolic functions of the cosine and the cosine. This equation can be simplified by replacing the exponential factors. We have the exponential factors, and we all know this exponential factors can be written in the form of a hyperbolic functions or the circular function. So, when we write this exponential functions in the terms of hyperbolic functions or the circular function, the hyperbolic function can be written as e to the power plus minus gamma z equal to cos h gamma z plus minus sin h gamma z. So, what we are able to do? Either we substitute this in this equation, what we are getting in the terms of load impedance and the characteristic impedance, or we will substitute this to this equation which we are getting in the terms of input impedance and the characteristic impedance. We can use either of the two or both, it depends upon us, because we can have the expression in the terms of hyperbolic in both the condition, and the same conditions is applied also when we are available with what type of parameters. Okay. So, let us do for the first case when we have the line impedance in the terms of input impedance of the line and the characteristic impedance. So, when that equation is in the equation 3 here. So, when we yields the line impedance at any point from the sending end in terms of hyperbolic function. So, when we substitute the hyperbolic function in the equation 3rd, we are able to get the line impedance at any point from the sending end in the terms of hyperbolic function. And when we substitute this condition into this equation 4, in that condition what we are getting? We are getting the line impedance at any point from the receiving end in the terms of hyperbolic function. So, first with the equation 3rd, that is from the sending end, when we substitute e to the power that is our exponential function with the hyperbolic function, we are able to get this function equation. So, students, it is also consider this as your task that you substitute this value in equation 3rd and 4th, equation 3rd and then to equation 4, and you are able to get these two expressions, that is first in the terms of what? Our line impedance in the terms of ZS and Z0, that means from the sending end in the terms of hyperbolic function, and this when the you are available with the ZL and the Z0 terms, and if you say that impedance, line impedance in the terms of our from ZL and Z0 from the receiving end in the terms of hyperbolic function. So, what the main conclusion which we are getting from this, that we have to take the line impedance equation very wisely. Very wisely means that what conditions you are with, and with which equation you are comfortable. So, here you are available with 4 type of equation of the line impedance. So, you have to choose the equation very wisely, that whatever equation you are choosing should have the parameters which is required in that equation, and the second thing, the calculation should be easy for you and you are very much comfortable with that. So, choose the equation of the line impedance very wisely. And now comes the condition for the lossless and the lossy medium. For a lossless line, when we have gamma is equal to j beta, we all know that for the lossless line, here, we know that our propagation constant is equal to alpha plus j beta, but for the lossless line this alpha is equal to beta. So, our gamma is equal to j beta. So, in that condition, what will be the change in the exponential function? We know sin at j beta for that condition will be equal to j sin beta z, and cos at j beta should be equal to cos beta z only. So, hyperbolic function changes into normal one. The impedance of a lossless transmission line in that case will be Z0 is equal to R0, and the expression changes. And how we will change the expression? We have this one, and now this our hyperbolic one in the terms of tan, and we will take further that equation, that is equation 3 and the 4 in the terms of ZS and Z0 and in the terms of ZL and Z0, and we will apply the condition for the lossless line, because the expression which we get in this particular slide is for the lossy medium, because here gamma exists and the gamma is equal to alpha plus j beta, which include both the attenuation and the phase shift. But in this slide we are talking about the equation when there is a lossless medium. In that lossless medium, our sin h j beta should changes into this, and the cos h j beta should changes into cos beta z for the lossless line. And when we substitute the expression, we have this expression. So, what is the difference between the, when we precisely look at it this, what is the difference between the lossless and the lossy? Just have a look. Zs minus Z0 tan h gamma z, and what we have here, Zs minus j R0 tan beta z. Gamma is replaced with the beta 1, okay, and here we have gamma z only. Similarly, this is in the term of Zs and the R0, and this is the term of Zl and the R0. So, these are the two equations in the terms of hyperbolic functions, in the terms of Zs, R0, in the terms of Zl, R0 for the lossless line. Thank you very much.